mad science talk for today. And our second speaker is Professor James Pustejovsky from Brandeis University. Professor Pustejovsky is DG ex-Felberg Professor of Computer Science at Brandeis University. Simultaneously, he is also the head of Linguistics Department, which is probably the rarest combination that you can think of. But he is among the most influential computer scientists, computational linguists, and experts in artificial intelligence. His interests range from theoretical and computational modeling of language, knowledge representation, simulation, semantics, and machine learning to formal representation of space and time, and event representation in particular, which is a link to our symposium. He's done groundbreaking work in computational modeling of structure of lexical knowledge by publishing the Generative Lexicon, MIT Press 95, and he's been elaborating numerous high-impact research articles. He's author of, co-author of more than 10 influential books in computer science, computational linguistics, artificial intelligence, and cognitive science. And his work integrates computer science with experimental cognitive science, philosophy, linguistics, and sometimes when I talk to my students, I mention Professor Pustejovsky as a good example for somebody who integrates in a truly interdisciplinary manner different areas without losing the high level of precision in each of them. So, and I'm pleased to welcome Professor Pustejovsky as a mad science speaker for our symposium.
Thanks, Yurgis. As one of the other speakers said, it's kind of hard to live up to that introduction. But I want to talk about this. I want to explain what this title means: visualizing meaning, this notion of semantic simulation of actions and events. I've been worrying about how to represent the events as expressed in language and thought for a long time. First, from a lexical, semantic, and a compositional perspective, then from a knowledge representation, AI perspective, and then most recently, over the last 8 to 10 years, combining that into somewhat more formal form into kind of modal logic perspective of how to model events and actions and have that still be kind of relevant to compositional semantics and computational semantics. But this is a mad science talk, so I'm not just going to give an exposition of my lab's research, although I'm going to. It's going to be in the context of something which is a bit more approachable. That's what, that was my charge, was to make something kind of a little bit less technical and more approachable. So I'm going to talk about human-computer and human-robot interactions. So we've been working within the context of HRI, human-robot interaction, applying techniques from computational modeling that are linguistic and cognitive-oriented towards issues in language and gesture communication for avatars and agents in games, as well as for robots, in a way that I believe can be seen as the beginning of a sort of new platform for how to model HRI systems. So we'll start with what I'm going to assume, which will be that for an agent or a robot, we're going to need robust recognition and generation with a lot of modalities. And here I mean the modalities of being able to understand language, to understand gesture, and perhaps proprioceptic and haptic and audio, and a lot of other modalities that we as humans take for granted, but also the ability to understand and generate language action. So we need to have some notion of action in a model. The framework that brings all this to kind of sort of a satisfiable end or implementation is a notion of contextual grounding and co-situatedness, which is implementation of the familiar term of common ground from philosophy and psychology. So what we have devised is a platform that allows for multimodal or creates multimodal simulations. And we can think of this as a way of helping us model human-computer interactions. So in AI and in computational linguistics, currently with the craze of deep learning and neural nets, there is this drive to perform what's called semantic grounding of language. Semantic grounding of language is don't just take a bunch of data from some 15 terabytes of text and do statistical analysis and create a nice model over that you can then use with multiple embeddings of glove and word2vec and use and Elmo and BERT and all these other sort of embeddings that we have just from text. If you're familiar with those terms, great. If you're not, it doesn't matter. They're just vectors. And we can understand what the meaning of a word is in context. You can do compositionality with sort of deep compositional semantics with vectors. Well, you still can't do everything because you don't have a grounding for what the actual vector refers to. So much of the community has focused on trying to visually ground words, or embeddings in this case, with other embeddings, which would be an image vector. So here's an example of what's called visual semantic role labeling. Identify bounding regions in an image. Imagine this per frame, so 30 frames per second. Imagine doing this in a sampling of every 3 frames in a video as well. And we're going to identify and semantically label these using some vectors from an image processing system. And we're going to link those to linguistic expressions, let's say in a caption. So let's say the caption of this is the batter hits the ball, or strikes out, or whatever it might be. So this is going to be a constraint from 2 modalities on how visual semantic roles, such as agent, patient, instrument, the bat, or maybe the catcher, or whatever the thing is you're trying to pick out is, how they're actually grounded relative to each other. Here's another example from the MC2 data set by Yatskar et al. So there's a whole set of jumping events, and they're labeled with semantic roles. And what you have is, in addition to an image, which has bounding boxes for, Michael, can I use your thing? So this is going to be captured, this is going to be some notion that this is a free fall, jump, whatever. And these are the roles with their values here. This is a different kind of jumping. So you differentiate the different word senses for a particular lexeme. And because the visual scene is not ambiguous, there's no lexeme, it's a visual region set. And so this helps us do semantic grounding. But semantic grounding only goes so far. So to understand language isn't really enough. We have to situate the grounding, which entails the knowledge of a situation, my goals, my intentions, as said earlier in the conference, and the contextualized entities as well. So, for example, here, I couldn't get this to work inside, so I'm just going to get this to work. There it is.
Hey Siri.
I'm listening.
What am I pointing at?
Interesting question, Karen.
That's not the answer you want. So that was my friend doing this to Siri. Anyone of you can do that. Siri and Alexa will give you the same answer, more or less. Interesting question. And they'll tell you your name, and you'll say, that's pretty bad. So this is an example of not having any access to the context, and not having even the roughest access to gesture. Now, Alexa, in your interaction with the Echo, that you may or may not have as the first foot in the door for Amazon to completely Internet of Things your kitchen and house. That's what Alexa is doing, right? The Echo is just collecting data, massive amounts of data, so Bezos can become even richer and richer. The data collection that the Echo is doing is still without any context. So next generations of these devices are probably going to have sensors where they can greet you when you come into the kitchen and say, "Hi, James, how was your sleep? Would you like the normal coffee?" Things like that. It'll be linked to your Internet of Things with everything in your refrigerator, et cetera, et cetera. Now, this is going to happen. That's neither here nor there. But in order to make that happen in a useful and meaningful way, not that I want it to happen, but it's going to happen, you need to actually have communication and common ground. So, in order to facilitate the common ground, we are studying very simple cases, to use Michael's expression. We're taking very simple models. So, not even the mouse model. We're taking yeast, okay? Not even, maybe E. coli or yeast as our model. Let's look at what a model for communication would be that can be multimodal and allow us to exercise as many of the parameters as possible. We want to identify all the genetic markers, if I was a biologist, okay? All the neurons. So we're talking about maybe an aplesia, if you know neuroscience. You can identify all the neurons in certain types of models. In our context, I don't want to have to think about an abstract model of presuppositions that the agent or co-agent can bring to bear to a situation. I want to know exactly what they are. So it's a very artificial environment, but that's what we're using in order to come up with the first examples of what peer-to-peer multimodal communication would be. So when we engage in dialogue, we share experience, we share common ground, and this is what allows us to have situated communication. When we take this out of our context of common ground, we can still communicate. We use decontextualized reference. That's the symbol grounding problem. And we're trying to learn how one can actually disassociate the context associated with a gesture, a lexeme, a smell, a context, and then reapply it in a new context where there is not that common ground. Now, this work implicates and touches on a lot of areas. I'm not going to go into the areas. I just want to mention that there are a lot of research disciplines that need to be brought to the service of such modeling. Mental simulations is actually first from the list. The notion of creating a simulation, which is essentially an embodied representation of the events that are transpiring. Taking a kind of computational notion of what embodiment is relative to my actions in the context, it needs to be taken out of the speculative textbook of much cognitive semantics and turned into operational computational models. Those are inspirations that we would like to draw on and actually make them effectively computational. Also, the mirror neuron hypothesis. I think the mirror system hypothesis is actually something which got me really excited. And Chris and I were at an RBIB event about a year and 2 months ago, where much of this discussion of communication and what inheres and what's required for communication between conspecifics allows us to actually effectively achieve our means of co-intentional activity. Simulation semantics, as first, I believe, articulated by Alvin Goldman, and the notion of mind reading is really critical for this model of understanding what you are doing as an agent. So, multimodal simulation is what I'm going to be talking about. It's contextualized 3D virtual realization of both the situational environment and the co-situated events. So this is built on a modeling language that we have, what's called BoxML, which is Visual Object Concept Modeling Language, which has a nice realization and a nice semantics. It encodes objects with semantic typing and action affordances. Actions are essentially multimodal programs, and essentially it helps us discover in a particular context what the common ground elements in a discourse are. And I think it offers a platform for studying how we interact, not just between humans and computers, but human to human as well. So let me give an example of, this is one example interaction between an artificial agent, what we call a synthetic robot. This is essentially the image of a brain for a real robot, as, let's say, exemplified by Matthias Scheutz's group at Tufts, who we're collaborating with. He's got actual robots. We have a synthetic robot brain for his actual robot. And what we're going to do is going to build something together. This takes about, I think it's about a minute. Let me just show this video. And then we're going to go under the hood.
Hello, Nicole.
Hello.
I'm ready to go.
Can you put the green block on the red block?
Okay.
Okay.
Do you mean the yellow one? Okay, go on. Should I push the yellow block right of the red block?
Yes.
Okay.
That one?
Which object do you mean the orange one?
Yes.
Okay, go on.
Put it there?
Should I put the orange block on the yellow block? Should I place this here?
Yes.
Okay.
Her arm looks a little painful there.
The black one?
Okay, go on. Okay.
On the green block?
Should I put the black block on the green block?
Yes.
Okay.
Now pick up the purple block.
Should I put the purple block on the yellow block?
Yes.
Okay.
And push the orange block left of the yellow block. That's it.
Okay, so
Bye.
goodbye. How do I get out of this? Let's see. Is that the right one right there? The, sorry? Mouse? Sorry? This one here? Okay, thank you. Got it. So, contributing to this effort are a lot of different areas, and I'm not going to reiterate what those are. But one thing I do want to mention in particular is that there's been some effort to take text and create images out of them, and very beautiful images, a program called Word's Eye that Coin developed along with Richard Sproat. It takes text and puts it into 3D scenes. It relies on a large 3D database models and poses, and it has shape displacements and things like that. This is different than that. This is different from 3D scene generation as well. We're doing this compositionally from the sort of denotative semantics of the objects in a way that I'll try to explain. So this is done in the context of a very large effort funded by DARPA called Communicating with Computers. And they're essentially the following hallmarks of communication that we need to satisfy. We need to be able to move the conversation forward. We need to make appropriate use of multiple modalities. We need to be able to steer the course of the interaction. We need to be able to reference the interactions based on frames of reference, different frames of reference. And we need to somehow demonstrate the knowledge of the changing situation dynamically. So in order to do this, we have a synthetic vision. We have machine vision and synthetic vision. We have language and gesture, recognized and generated. We have a dialogue manager that is managing the state machine of where I am in a dialogue. We can basically ask for clarification. I can guide for specific types of goals. We have what's called an ensemble reference using Deixis language and frames of reference, which is a multimodal continuation semantics. And then basically we want to visualize the epistemic state, the dynamic epistemic state of the agents as we move through the dialogue. And that's called episem, which is something. So here's the architecture, just real briefly. I've got live gesturing and speech. I have a connect, or several connect cameras, which give me then feed into an 11-layer convolutional neural net system with our colleagues at Colorado State University, Bruce Draper and Ross Beveridge, that delivers to us essentially a ranking of classifications of the gesture types, about 35 different gestures. At the same time, we have a speech model which recognizes the speech. So we have the DCNN gesture recognition. It's put together with the semantic package from the speech recognition. We actually integrate that into the state information in voxsim is called, and then basically do our action. We create some action. So I'm going to go into the hood of that demo to show you exactly what's going on. So the architecture of Vox World consists of several different models. We have a dynamic interpretation of actions and acts, communicative acts, based on a dynamic temporal logic. We have a dialogue manager. We have this visual object concept modeling language I told you about. We have a visualization of the epistemic state, which involves a set of what we call public logics. So we have a public announcement logic and a public perception logic. And then we visualize everything in terms of this 3D Unity game engine system, where everything essentially is rendered as an actual virtual simulation. We do that in order to uncover the presuppositions of discourse. So the logic is essentially a fairly straightforward reduced first-order dynamic logic, where I basically want to modify an object's location, its size, its color if I can, whatever sort of attribute is changeable. And an event is modeled as a sequence of frames. I have change of assignment and values, which allows me to essentially say that the location of this block has been changed to location xy to x prime, y prime, for example. And so in a basic lexical structure, I would have die being encoded as the opposition of going from not dead to dead, for example. But more to the point for locations, arriving is going from being at one location to being at a designated location of interest. Arrive here at the conference, for example. So there's essentially two primitive event types. I have states in a basic simple transition, as in a kind of label transition system. And then I can derive the vendor types by compositional structures from those. And I'll talk probably more about that tomorrow during my event location talk. The language of VoxML is a modeling language which essentially allows us to create a type for the geometry of an object along with its semantic ontological type. And it encodes dynamic semantics of nominals, which are objects, events, which are usually programs, and adjectives, which are going to be object properties. The individual data structure is called a voxeme, parallel to a lexeme, and the collection is a voxicon. It's a visual instantiation of a lexeme. It will actually eventually have acoustic and proprioceptic and haptic information when we have such things. We already have some audio information for some concepts. The idea is to think of it as a scaffolding for simulating objects and for operationalizing behavior. It also encodes two notions of affordances for psychologists, ecological psychologists and roboticists in the room. Gibsonian, which is something can be grasped or reached or moved, and something I call a telic affordance, which is what can I actually do with this? I can drink from it, I can write with it, I can read it, I can throw it, for example. So a voxeme has a geometry structure. It's an object characterization in R3 space. It has what's called a habitat, which encodes its orientation, its default orientation, situated context, the scaling relative to the agent. So it's going to vary depending on who is the agent model. And then the affordance structure. What can I do with it? What can I do with it? And what does it actually enable? So I get some kind of transitive relationships for affordances when I compose them. So here's an example of a knife with its geometry. It has a structure of a rectangular prism. It has two components. It's an asymmetric rectangular prism object. It has a handle and a blade. It has a kind of flat concavity, and it has properties of rotational and reflectional symmetry, which are important for how we want to reason about it spatially. Furthermore, the habitat structure, which I'm not going to go into great detail about, tells me where to hold it and where to use it for what I can call its telic purpose, which is to spread or cut, whatever it might be. It tells about the scaling as well. Here's a cup. Cup is going to be a cylindroid. It has a property of being concavity oriented, which enables several things. The top of it allows for general support, like a block would, but also it has concavity, which would allow support of something in it, such as in the contain relationship. So it also says that I can grasp it and roll it if I have the right symmetry, or the right axis picked out. Okay. Verbs are programs, So grasp happens to be a primitive, but I basically am going to analyze them as state-to-state transforms, which can iterate or can culminate and have some kind of satisfaction with a fixed point test. And we compose these with a continuation style semantics, which essentially takes the semantics of the cup and the semantics of the grasp and basically creates a grasping cup action that I'll talk about a little bit later. And this is kind of the dynamic interpretation all rolled into one of what the continuations are. Once I get the cup, I put it together with the grasping. What can I do with them? It's going to basically have a kind of continuation interpretation. Okay. We make a distinction between an object model and an action model. Together they make an event model. This is important for a number of reasons. It allows us to focus on what the state-by-state characterization of an object is as it changes. And the action model is going to be everything affected by the intentional agent and how she changes the world through her action effectors. The action, the agent essentially is a controller of a number of instruments, including the default instruments of hand, but also possibly any other part of her body, and possibly other instruments that come with that, such as a knife or a fork or a hammer or a pen. So in order to get this embedded within a situation where we can study how things move and how things change, we're going to define a simple implementation of common ground. So common ground has been the starting point for how to essentially handle presupposition, accommodation, bridging phenomena, as well as many other effects within formal semantics and pragmatics and philosophy. We will step back a bit just for today's lecture and talk about what we actually assume or presuppose with common ground. We're going to think of it as the ability to co-situate and co-perceive what we have in our environment, which are going to be anchors. The anchors are going to come from language, from gesture, and actually from the product of identifying the results of an action, and as well as gaze. Intonation, of course, could also be big for this. So we distinguish between shared experiences and shared actions. An experience is something like we hear the thunder outside, or we feel the rumbling of the room upstairs because of the loud music or something. But co-intention and co-attention come in when we're actually sharing a goal. And we also have shared situational references. So we assume a basic kind of Cooper-like situational type structure for records, and we have an agent engaged in communication. There's going to be a set of agents, a shared belief space, and then we have the local objects and relations that are going to be jointly perceived in the environment. So that's going to be P. And then we have the embedding space, which I'll talk about in a second, which both conspecifics embody in the communication. So this is just a simple example. I have the speech, the utterance of you see it, and it identifies a particular agent, and referent to a particular object B, a discourse referent B, which is actually still perceived. So events and objects, as we experience them, are going to be distinct from how you can refer to them, right? Because we can package and quantify, measure, and order experiences in a way that are very abstract and distinct from the way we actually see them presented in context. The language mechanisms allow us to do this in a way which has to be made transparent in my discourse. So the surface realization of this is usually language, but it can also be gesture. So we'll distinguish, we'll see all of these, not all of these, but most of these in the communicative examples as I go under the hood for this. Atomic communicative acts such as warning, inviting, and greeting, and then the complex ones, which are informing, asking questions, giving an imperative, and making promises. Okay, so we structure a communicative act as basically a pair, for now, of a speech utterance, and presumably with the appropriate intonational contour and a gesture. And so we study these three configurations and see what is actually missed or provided by one versus the other. So we have a small gesture grammar, which has intonations along with it. We have a pure gesture grammar, and then we have the combination of the two, which I'll talk about today. This is work that basically got inspired by the workshop that I spoke about earlier with Michael Arbib, where Chris was, which was about primate and primate language, communication and development of human language. So simulations is the preferred way of modeling this because unlike formal models, which provide a nice reasoning platform for a computer, such as minimal finite models, they allow us to do inference, set resolution. They're not effective media for communicating with humans. Communication is facilitated through semiotic structures that we share and we understand. But we use the modality of vision and the representation of something visually to effectively demonstrate what the agent or the robot actually knows and believes and sees. And this is, in my mind, the best way to actually communicate and demonstrate what the current epistemic state of a robot would be. So, in this example, let's go under the hood.
Can you put the green block on the red block?
So it's no gesture, definite description.
Okay.
Okay. So that was just a basic speech recognition with an incremental parser, semantic interpretation of the output, and then referential grounding very straightforwardly to something in the context.
Do you mean the yellow one?
So that's just gesture.
Okay, go on.
Acknowledgement was also through gesture. So there, we have this gesture recognition system coming from this 11-layered convolutional net system. And then we do incremental parsing on that output. We take the interpretation of the gesture signal and then ground to something in the context, as I mentioned. So gesture has a grammar, and this comes essentially from Kendon's work, as formalized a little bit, actually quite a bit, by Alex and Matt, Lesgrees and Stone and others, where you have essentially one core component of a gesture, which is going to be the stroke, and then of course the end of the stroke, the retraction. And it's the content-bearing phase, which is the denotatum. And so, for example, a pointing, a deixis, is going to essentially be, take the terminus of the cone trace, so trace the cone by virtue of this particular activity, this particular act, the vector. And we have a lot of gestures that I can talk about in a second. So we have a gesture grammar, which we can actually then create as a simple grammar, which has a very straightforward semantics. Deixis allows me to have an object of my deixis, the pointing. An affordance pair essentially is some type of activity with an object implicated, and then I can put it in the common ground and then say the object that I'm pointing to is actually already referenced in the common ground, or it's not. In this case it is because it's B1. I can have gestures denoting affordances, such as grabbing, pushing, and throwing. Here I have an imperative which impacts the other partner in my communication, A1, which basically says I have to have an imperative which is signaled by A2, for example, so I'm the person actually giving this directive. Then I can put them together. So this essentially is a gesture sequence, and this basically is two gestures, a deixis and grabbing. So I say like that, grab, okay? It's a sequence. I take it in sequence. The semantics of it basically says I need to go take the specification of where I was pointing and take that to be the object that's grabbed. The grab is essentially, as you might say, kind of a null object construction. There's nothing there to grab. I have to take the value from the pointing. Gesture, of course, has this all over the place. And here's the case with 3, so I could say, here, the deixis has two interpretations. It's taking the object in a particular region, and the other case, it's actually taking the region without the object. So, deixis, the denotation of deixis is actually ambiguous. It's actually a polysemy. It's actually, I think of it as kind of the or dot object, or complex type. It's both the region and the object contained within the region if there is one. So here, let's take an ensemble, which is the collection of multiple modalities.
That one?
So
Which object do you mean the orange one?
So that's the disinformation
Yes.
on the basis of that.
Okay, go on.
Put it there.
Should I put the orange block on the yellow block? Should I place this here?
Yes.
Okay.
So there was a locational deixis and clarification. And so multimodal communicative act essentially is something we call an ensemble of gesture and speech. And in this case, we take gesture to be the driving syntax and semantic, so it's called co-gestural speech instead of co-speech gesture. It's multimodal communication with both of these that have to be aligned. So the alignment is indicated by the vertical dotted line. That's done, well, I won't get into the technical details of how that's done unless somebody asks me. And so here's an example of the utterance of that with deixis, and then an affordance. So I say that. Okay, so not both gestures have a linguistic utterance, just one. This would be that grab, just simple alignment. This is trivial stuff, but we need to have some kind of very simple model to start with in terms of what's the gesture syntax and semantics, how do I put this together with a very simple multi-word grammar, and then how do I unify the continuational variables for both streams of input and make them consistent with one another, and then come up with a new continuation variable for the ensemble itself. And here's one with the third one. So move that, so that move there. Okay, you get that. So we could do that till the cows come home, but we don't have that kind of time. Let's see, what happened? I think, here we go, I think. Now let's go do...
Should I push the yellow block right of the red block?
Yes.
Okay.
So, and push the orange block left of the yellow block.
So deixis, it doesn't need to be disambiguated in terms of its frame of reference, but if you do actually use a referring expression, you need to make sure you're aligned with your agent, your co-agent's interpretation of which frame of reference you're taking. And in fact, we are modeling this on the basis of user studies done at University of Florida, Gainesville, by our colleagues in the grant work that have looked at human-human interactions and turn-taking for which frame of reference is being used. And this aligns with work that I believe Simon Dobnik has done in Gothenburg, and work that David Traum and others have done in terms of dialogue turn-taking, and it's settling on a particular frame of reference. It's independently very difficult work to actually model, but we're stealing from the best people in the field. So gesture is going to be directly grounded to an orientation, and the human adopts the avatar's frame of reference for the next command, if that's what she proposes. So basically, under the hood for the epistemic states, let me just briefly go through that. We want to visualize what the agent knows and sees and is in a context, and maybe hears, but we only have hearing by virtue of the speech recognition system, not in terms of non-speech acoustics. So, for example, a bell or a train or a dog. So for that we use the EPDL version for public announcement logic, so epistemic PDL, propositional dynamic logic, which is a very nice and easy to use propositional-based logic for doing dynamic updating in fairly sophisticated contexts. And then we developed something which is analogous to that called public perception logic, which is for seeing. So I'm just going to give you an example of what's happening in the dialogue.
White one?
This is kind of hard to see, but this is where I am.
Go on.
State-to-state transformations in the large...
Should I put the white block on the purple block? Should I put the white block on the red block? Okay.
Now, as you might imagine, if you've ever built an actual dialogue system, you have to encode the possible turns that you take in a dialogue, and it's frustrating if you're a formal semanticist or someone who actually does real pragmatics, because you don't imagine that that's what we do, but I think we do need some kind of model of that, and it's humbling, if nothing else, to have to come up with all the possible options for what I might actually do, say, hear, etc., etc. So public announcement logic basically models the knowledge of agents, I take this to be essentially this box A, essentially an agent is taken as the set of all accessibility relationships, which basically that's the indistinguishability relationship. So A knows that P, and I can know complicated things, and I can also announce things. So this thing which has the exclamation point essentially is an announcement. I say, I hereby tell you X. And by virtue of that, not only do you know X, but you also perhaps know Y, which results from it by inference or by some sort of entailment. And then the last thing is basically presupposition, which my students call the duh phrase, something that everybody knows, duh. And so this is an example of Diana, who is the avatar, and the human. This is the transitive closure of all the agents. And so we can presuppose that all the agents in a particular communication environment will know the proposition phi. So, for example, Diana knows how to point. The human knows that Diana's at the table. The presupposition phi holds. And then I can do what is called assertion in the common ground, which, given the presupposition of phi, I can actually say psi and then assert something that is new. This is the way of doing new information. Okay? Very straightforward. We can do the same thing for perception. So the synthetic vision basically is a vision agent is encoded as a set of accessibility relationships between situations. But it has to take propositions. So if I want to just say, I see this pointer, I have to propositionalize it, that the pointer is there. And so basically this is like saying A can perceive P, agent A perceives that there's an X. And then the same thing, I can make a public perception. I can reveal something so that everyone can see it. So I can open up the box. In the example this morning, between the two women who were doing the experiment with the child, she was opening up the box for the other person. And I can also do the presupposition of perception. So if we all see this screen, we don't really have to mention it in the appropriate way because it's commonly perceived. It's publicly and commonly perceived by everyone here. So it's the perceptual common ground. Everyone can see that there's a screen there. Okay, so it's hard to visualize at the Epistemic update, but we have essentially an eye view and a brain view. So this is what I can see. So we made the white block disappear. Okay. Now
White one?
Okay. Holy cow. What happened to the white block?
She is surprised by the white block not being there.
Okay, never mind.
Now we're going to put the white block back.
Green one?
Okay, go on. Okay. I didn't know that white block was there.
So you get the idea. The surprise on both sides, knowing something that appeared that wasn't there before, and something disappeared where it should have had some kind of object permanency or inertial grounding and stay in the situation. So Okay, so this is one example of the type of communication we're doing with synthetic robots, and then put this as the control strategies and control structure into actual robots. Let me just talk really briefly about learning by communication. So this is a very rich platform. It started off as essentially an embellishment, a small embellishment from event models that I had worked on many years ago, and it became something rather more than that. It became a way of actually trying to create a platform for communication with synthetic robots or robots by virtue of the one principle, which is demonstrate what you know and what you see. So the simulation is the mind reading of the robot. And by mind reading, I'm able to actually know what the robot is seeing, and for all intents and purposes, relative to a certain number of situations, what it thinks. And I believe this is actually potentially an interface for smart devices. This type of simulation, multimodal simulation, could be the foundation for interface design. But in order to do that, we need to have it be fairly robust and to not just hand code everything, but to learn the affordances, to learn the behaviors, to learn concepts, to do a lot of learning. So we're looking at concept and object learning. So we've been learning by demonstration. I had a PhD student, Do Tuan, who is now making lots more money than I am at Google, who learned the concept of slide around using, this is a nice integration of using several types of neural net architectures with qualitative spatial reasoning models, such as an orientation calculus. If you know some of the things which are richer than RCC8, we heard Ilga talk about RCC8 relationships in a talk earlier today. The orientation, so Frex's calculus, OPRA, all these various types of calculi which give rise to the identification of quadrants or regions in a particular space, 2D space, and basically allow me to do reasoning through a composition table over where an object is relative to something else. For learning how to push something around, rather than having to learn through thousands and thousands and thousands of samples, if I'm doing something like an LSTM, a sequence-based learning model, neural net model, I can actually just satisfy the contiguity constraints of region to region to region to region. Okay? So, and so you've been able to kind of abstract away what's actually the important part of a round. Well, either direction works, and it can be like this or whatever, and you can look at, we can talk about the details of that. But what's important is the contiguity of all the regions such that there's no gap. All right? And that's what the integration of the QSR, qualitative spatial reasoning component, does. Another thing that we're doing is learning from interactions. So we took many of my students from many of my classes and made them teach Diana how to build a staircase. And so they weren't graded on this, but they were given extra credit for it. And essentially, we allow them to interact with the development of how someone is constructing something. Let me go into a little bit more detail of that. So I have CNN predicts the most likely target configuration from the data that we've collected. That's actually classification, saying, oh, you're this, or you're this. LSTM is like a hidden Markov model in neural nets, or CRF, conditional random field. Basically, it's a sequencing predictor, and it predicts what the remaining sequence of moves would be. You could link that up together with Carla's possible continuations in your event model. And then we do heuristic pruning on the intersections of the two sets. So, in any case, what we got was, here's a learned staircase. And this is her generating a staircase on the basis of the model. This is just one example. It's not great. We'd like her to maybe push it a little closer. Okay? So what we're doing now is intervening with language, saying, no, wait, hold on, Diana. Let's try to make that a little bit better. So if we could, for example, correct an incorrect example by saying, you know, if you move that block over there, you'd actually have a staircase. But we're doing that through language. So why have to retrain that? Why have to go through another 1,000 iterations, or do some kind of convoluted policy learning with a reinforcement learning? Just tell her what she needs to do. And the communication is extremely succinct and very useful. That's what's called multimodal learning. We're currently learning different affordances for different kinds of objects. So how you hold something depends on what you want to do with it, and what kind of object it is, what the basic geometry of it is, whether it's symmetric or asymmetric, whether it has a function, whether you recognize the function, whether you can recognize the handle, and what you want to do with it. Do you want to hand it to somebody so they can use it, or do you want to use it? Or do you want to put it away? Or do you want to wash it? All these things are very different. They're different habitats. I want to use the knife to spread versus cut versus put it in the dishwasher versus hand it to you. The way you're going to hold something, of course, is very different. So we learn different kinds of affordances for different objects. And this is where we're integrating with Matthias's group, Scheutz, with his one-shot learning through task-based natural language dialogues. So he has also he creates simulations from observing humans pick up various kinds of objects. And what we're doing together is using our simulations to learn by communication through dialogues, to speed that process up of learning and exploit the semantics that we have of affordances and programs to essentially improve and optimize the way things can be picked up, things can be moved, things can be supported. So, kind of slightly different nature of a talk than what we've heard so far, but I think it's entirely related to the cognitive origin and cognitive modeling of events and actions. That's what makes this a very, I think, unique approach and I believe platform for doing HCI and HRI, because we're actually looking at what humans do. We're trying to model what we do when we understand each other, when talking and acting together and understanding each other's actions and communications. The flip side of that is that the simulation is actually both a model and a platform for studying common ground. I think this is kind of it's kind of a platform where we can play with ideas and set parameters and break it and add to it and sully the water and just see what we need to do to make it more and more complicated. So these models need more data. So we're getting language image corpora and language video corpora for training, which is what you have to do in order to make such things essentially scalable. And that's pretty much it. Thanks for listening.
Thanks a lot. Questions, comments? Rob?
So, great talk. I guess I have a question related to whether you're taking your general approach as normative versus descriptive. I guess, given what you were saying at the end, you're interested in what people do. I'm taking this more as a kind of descriptive account. But then I'm sort of influenced by like Boaz, Kazar, and people who are arguing that there's difficulties achieving common ground, and sometimes speakers will selfishly, egocentrically talk about a cylinder next to a red pyramid, even though they don't stop to think that the listener doesn't have access to that red pyramid. So to what extent are you interested in incorporating those kind of components?
Great question. Very, very interested. We're going to do it very slowly. So if we don't have the situation which actually satisfies the description in that example, that's one example you just gave, right? So yeah, then we need to correct and accommodate to the common ground. And that's one thing that we're just now working on, which of course is what semanticists have been doing for the last 30, 35 years, accommodating to the common ground. To do that, I want to have as many of the parameters in the multiple modalities and what I have in my epistemic store as fixed as possible, so that I can look at the path of exploration, the exploratory paths for how I would actually accommodate. And then I think very much what happens, you can start operationalizing some of the theories, if not some of the algorithms that exist for accommodation, for example. And so that's a very good question. That's what we're getting at now. Yeah. And then after that would be the real displaced reference, right? Where you're just talking about things that are not in the common ground whatsoever. And you need to have effectively learned that concept or be able to kind of get by with generalizations of what you're talking about in terms of conceptualizing what that geometry might be by virtue of how you're holding it. So if I say I was holding this glog yesterday and I broke it, right? This kind of typical examples from cognitive science where you know it was holdable, so the affordance was that it was somehow capturable in my hand and it was breakable, things like that. So those types of inferences, which are just common sense, are completely beyond the ken of the current machine learning tasks. Right?
Thanks. Any other questions, comments?
I think Chris would have one.
Yeah, thank you very much for a very stimulating talk, and there was an awful lot in there to take in a single lecture. But I do have a question about a kind of foundational question, which is the parsing of events, actions, and also the annotation, if you like, of the affordances of objects is all done essentially by hand, right, as I understand it.
Currently, yeah.
Currently.
Well, actually, some of the affordances...
Now, yeah, this is actually my question, and that is, are you working on how this parsing can actually be learned?
Yeah, very, very deep question. The first distinctions we've made in terms of recognizing types of events would be the Actionsart distinction between a process and some type of culmination. And so that had to be done through essentially the application of an LSTM and then a CNN. So the classification of this being, oh, I'm essentially at a fixed point, I've satisfied my constraint, I'm not going anywhere, so I've actually, the ball has reached the wall, or whatever it might be. So I have effectively an accomplishment, to put it in linguistic Actionsart terms, versus a process of just continuing to move. So that basic distinction was the core of Tuan Do's dissertation. We learned that. Well, Diana, the synthetic robot, learned that. That's just a basic event type. Learning a state would probably be fairly trivial. Putting the rest of them together. So the type distinctions with certain types of objects have to be, they add new dimensional complexity. So what I can do, so learning rolling versus sliding, for example, is also something you can do if you recognize the boundary and how the boundary is actually moving relative from frame to frame along an axis, a rotational movement along the particular axis. So we're currently working on rolling versus sliding to actually robustly recognize that. These are really trivial, and I don't know the child language development literature terribly well, although I've been starting to work with Josh Hartshorn a little bit at Boston College, and he says these things come really fast, really early. What's the date on that? I don't know, probably 6 months. They already have these things. If you were to slide a ball versus roll a ball, those are probably really different. You probably have some surprise if you could actually see that something that should roll is actually sliding. In any case, those are basic distinctions that we need to learn as well. Yeah. So your question was, can you possibly learn all this stuff? Probably not, but we need to start somewhere, and we need.
But the developmental question is kind of is central to this, because there is, I mean, going back to Amanda's talk this morning, there is a great deal of evidence that that very young infants are able to parse events in terms of causality, spatial relationships, intentionality of action, and so on. So there is a really interesting question about whether you're simply matching semantic roles onto pre-existing event.
So the core question there.
Roles,
absolutely.
You got it.
Is what actually are going to the primitives be for such learning? And I'm assuming that the child, in such cases, is not going to get anywhere with just pure multi-layered neural nets. You've got primitives of ordering, of difference, of equality, of notions of different types of scales, and various types of models, which are going to be probably some primitive geometry and some primitive topology. I think there's going to be that's part of, I believe, the developing cortex or the developing brain generally, and we need to model that. So part of the project has been to work with 3 other sites to encode those basic relationships. They're called semantic primitives, right, in semantics, and that's one thing that we rely on. You would do In fact, one of the people on our team is Scott Friedman, who is Forbes's and Dedra's student at Northwestern, and he's basically doing analogical spatial-based reasoning over these types of things to say, okay, the notion of horizontal dimensional precedence can be related to vertical, or whatever it might be. Yeah. Very early days for that type of generalization or analogical reasoning. Yeah.
Okay, so thanks a lot. It was a wonderful talk, a wonderful interaction, and let's thank our speaker again.
Thank you.
Now it's time for coffee.